This is test number 2, question number 3 on the practice test, and the question is 100 grams of water at 80 degrees Celsius is added to 100 grams of water at 20 degrees Celsius in a styrofoam cup. The final temperature of the mixture is 30 degrees Celsius, and the question is, what is the heat capacity of the styrofoam cup? And you're given that the specific heat of water is 4.184 joules per gram degree Celsius. And so this problem is just a straightforward application of the zeroth law. And so we start with that. Q lost equals minus Q gained. We don't want to offend the energy rights activists. No energy can be created or destroyed in any process. And so the heat that is lost by the hot body is equal in magnitude but opposite in sign from the heat gained by the cold body. So we need to just simply identify the hot body and the cold body and then express everything in those terms. Now, the hot body is the 80-degree water, and the cold body consists of the 20-degree water and the styrofoam cup, because the styrofoam cup contains water at 20 degrees and 80-degree water is added to it. And so we start with that. And so I have 100 grams, and the specific heat is 4.184 joules per gram degree Celsius. And now, what's the temperature change? So we're going to need two temperatures. The delta T hot is equal to in other words, the temperature change of the hot body is equal to the final temperature, 30 degrees Celsius minus 80 degrees Celsius equals minus 50 degrees Celsius. And the temperature change of the cold body is 30 degrees Celsius minus 20 degrees Celsius equals 10 degrees Celsius. So now that we have that information, this is times minus 50 degrees Celsius. In other words, the hot body is 100 grams, has a mass of 100 grams, the heat capacity 4.184 joules per gram degree Celsius, and the change in temperature, delta T, is minus 50 degrees Celsius. And that is equal and opposite in sign. We'll place a bracket here because everything in the cold body is now going to be expressed. And so let's illustrate that. This is the heat lost by the hot body. And now the cold body consists of 100 grams of water, 4.184 joules for every gram degree Celsius. And the change in temperature is 10 degrees Celsius. So that is the mass of the cold water times the heat capacity, specific heat of the cold water, 4.184 joules per gram degree Celsius, times the temperature change of the cold water, which is 10 degrees. And the other cold body is the cup. I'll write that as C cup times 10 degrees Celsius and close the brackets. Now that is the heat gained by the cold body, cold water and the cup. Now we can solve for the heat capacity of the cup. And so this is pretty straightforward. 100 times 4.184, we move the decimal point over, it's 418.4 joules per gram degree Celsius. And then that is multiplied times 50 degrees Celsius. I can do that several ways. We can simply multiply it through Or I could take advantage of the fact that 50 degrees is half of 100, so I can multiply it times 100 and move the decimal point over 2 more places and divide by 2. And that's something I could probably do in my head, because if I move this 1, 2, 3, 4, it's 41,840 joules, and divide that by 2. So 41,000 on my scratch paper, 41,840 divided by 2 is 2, 0, 9, 2, wait, 9, 2, 0. So I end up with minus 20,920 joules is equal and opposite to. And now I do the same thing here, and this is going to be even easier because I have nothing but ones. So I have 100 times 4.184 is 418.4. 418.4 times 10 is 4,184. So it's minus 4,184 joules. And now I have to distribute. And this is the major issue that I see when people do this calculation. They fail to distribute this negative sign through the brackets. So that is minus C cup times 10 degrees Celsius. And now we just simply solve for C cup, which is, I have to add 4,184 joules to both sides. And so that I'm going to do over here. And that is 6. This is 3. This is 7. And this is 16. So minus 16,736 joules is equal to minus C cup times 10 degrees Celsius. And all that remains to be done now is simply divide both sides by 10 degrees Celsius. So, and the minus sign cancels. So 16,736 joules divided by 10 degrees Celsius is equal to C. And now that's easily done. Again, all I have to do is move the decimal point over 1, and I've got it. So it's 1,673.6 joules per degree Celsius is equal to the heat capacity of the cup. You always will get a positive heat capacity. If you get a negative heat capacity, one of two things is true. Either you've just solved the energy crisis, and we now can have unlimited energy from our styrofoam cup, or you made a mistake with the sign convention. And the first place I always look when I end up with a negative heat capacity here is right up here. I failed to distribute that minus sign through the brackets. And otherwise, this is very straightforward. You just take the zeroth law and go and keep everything on the left of the decimal point for the hot body, everything on the right for the cold body. You just come right down. Your logic is easy to follow, and it's clear.